Okay, 6 p.m. at PST. Let's get started. Today we are going to do this midterm review. It will be mainly based on the questions you have on the discussion, and then if you have any other questions live that I'll try to answer. Main thing, one from Troy is more about jump address, next address after a J call. Troy, can you please, if you are there, let me see. Yeah, Troy, can you please explain, like, what do you want to know? Like, what is the next address after J call means what?
Yeah, there was a question in the quiz where it was a jump and then it said an address and then it asked what was the next address that it would execute.
Oh, okay. So that question, it is not an ad, means it is the, what I have given in that code is that address part of the machine code. Remember the J jump instruction has two parts. One is the opcode, other is the jump address. So that 26-bit pattern I have given you through that hex number. So question become like, if we have that that bit pattern in the machine code, what is going to be the address, next instruction address going to be? So that's the question. Okay, I'll try to explain that. All right. And how do you develop a machine code for a call with a label in immediate field? So are you talking mostly about the BNE, those kind of instruction, B equal, where it involves a label?
Yeah, a branching instruction.
Branching instruction, right? Yeah, I will discuss that. But remember, like in a pseudocode, there can be other instruction, which is not a branch instruction, involve the label. For example, LI, load immediate, load address, LA. That's a pseudo instruction provided by assembler. And what you're talking about is basically how do we use that label in that LA instruction, which is very easy. It is basically, it's telling assembler that, hey, calculate the label, address of the label, and put that address value onto the register. That's the LA function. And other pseudo instruction can have involved the label, but branch instructions with a label, that's most interesting, because there is an underlying assumption of how that information being used and what would be the machine code needs to be constructed by assembler so that the processor can execute that instruction successfully. Okay, so that's very intimate conception there. We need to focus on that. I will explain it. Okay, there is one from Ricky, and I think Rahul wanted did some comment on that. Yeah, Rahul, I think you are correct in a way. Another reason that we have a zero register is think how you are going to initialize some values to, like some values, some register values to some specific decimal number, right? The easiest way it can be done is through addition immediate with respect to a zero register and some immediate value. Let's say you want to initialize some register S0 to a value of 5, right? Easiest way to do it is add I $S0, comma $0, comma 5. So it will add that immediate value 5 on the register value, constant register value 0. and give your initialization of that S0 register to 5. You can say, hey, I can use LI, load immediate, but load immediate, if it is a less than 16-bit value, it uses add-i as a basic function. So li is not a basic function, it's a pseudo function. So that's the reason, like it is mostly used by this assembler, in a sense, like people used to initialize these values with this pseudo instruction of li, and then assembler translate it as an add I on that register with respect to 0, some immediate value. Make sense, Ricky? Do you agree?
Yeah, that makes sense. I guess a follow-up question would be, so does that mean we generally should try to use basic instructions over pseudo instructions when possible?
That's my preference. I would suggest it because, again, remember, our motivation is not to be a mastermind in assembly programming, but try to use the assembly codes to understand the underlying the hardware. So if we write code as much close to as the hardware, which means the basic instructions, then it will be much easier. Otherwise, like pseudo instruction will expand your code into some basic instructions. You you may have a little bit difficult time to follow through what assembler did there and then what the hardware is doing. So that's my preference. But yeah,
Okay.
you can use the pseudocode if you like.
All right, makes sense. Thank you.
Okay, the other one from you is RT storage code aside from FP SPRA. Uh, yeah, Raul is right there. If we don't use it, don't no need to store it. Means use in the sense if we don't write it, we can read it from there. No one is preventing you to do that. But if you override the value with a new value on those registers, then you must store it under the frame. Otherwise, you don't need to. Okay, Ricky, that's okay then?
Yeah, makes sense.
Okay, we addressed both of your questions. Then let's get back to Troy's question. Let's start with the BNE, like jump, test and jump instruction. So what I'm going to share my whiteboard with you guys. And let's take that example and see what is going on there. Yeah, I started recording, right? Yeah, okay. So this example, I kind of put the BNE instruction in the middle. And let's say it has started some more instruction at the beginning and some more instruction towards the end. At the middle, we have a BNE, which is, in this example, it is jumping back to L1. So, and the other instruction is not important, just instruction, some instruction code. One important thing to note, the indexes. I said for the forward, like next instruction, like from the BNE with the forward jumping scenario, I index them like a 1, instruction 1, instruction 2, instruction 3. The away it goes after that, it becomes index become more. And then the other part, which is like if I want to jump back, that kind of previous instructions, I index like this is instruction -1, then -2, then -3, and instruction -4. So this is how I place the indices, just to make sure we understand the relative positions of the instruction with respect to the jump and test and jump instruction like BNE given at this specific address. And also we mark down their addresses. So this is important. You should be able to write for at least for the small code, write all the addresses up front, like side by side. This is just keep on adding 4 on for each of these instructions. So it's become 48C10141811C20, etc. So I put the addresses corresponding to the instruction. Now question become, how do I construct the machine code for this instruction involving this level L1? First of all, we know the L1 address, and that means my PC next is going to be, so from that instruction, my PC next is going to be that address 0 400 0000. And my current PC, that also we know, because it is executing this instruction BNE, which is at 0 400 0010. Okay. Now from here, what we all need to do is to solve this equation. PC next equal to PC current plus 4 plus branch address. This is known, this is known. We are calculating this BA. Let's do that. So this one then would become BA equals PC next minus PC current minus 4. Okay, which means we do replace with the value. Okay, use a hexadecimal calculator. There are apps in your smartphone as well for that hex value calculation. You can use that. That's okay. So let's do it. 0 4 1 2 1 2 3 4 minus 0 4 1 2 3 0 0 1 0, which is like in decimal minus 16 minus 4, which is like minus 20. Okay, minus 20. Now, is it okay? Like BA minus PC current minus 4. Okay, this seems like okay. And then the question becomes, what is my immediate 16-bit, right? We are basically focusing on this bit pattern. What should I put there? BA is one intermediate step to compute. This is 20. Now you see the BA is basically a bit pattern, a 32-bit pattern, which has to be the MSB extension 14-bit of the immediate 16-bit pattern, followed by that immediate 16-bit pattern, followed by 200. Okay? So this guy, let's exploit the BA's bit pattern, right? So this guy is a minus 20. That means it will be in 32 bits. 32-bit pattern BA is FF 2 3 4 16-bit 24-bit. How many bits? 1 2 3 4 5 6 7 28-bit, 4 more, FFEC. EC. So that's your 32-bit hex format. If you expand -20 into a 2's complement 32-bit form, you'll get a hex bit pattern like this, which is in a binary, it will be something like this. 1 1 1 1 1 1. How many ones I did? 1 2 3 4 5 6 7 8. Oh, sorry. My bad. Wait a minute. This is not I put some more bits there. This is, each of them become 4. 16, oh, sorry, my bad. Sorry to put that scary thing there. It's like this. This is F, 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 F. Okay, this is F, 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 F. Now E and C. C is this. Now is it 20? Is it 32-bit? Let's count. 4, 8, 12, 16, 20, 24, 28, 32. Okay, good. Now here, so this is my 32-bit. Out of that, 14-bit would be my immediate values replication. So let's take out 14-bit out of it. 4, 4, 8, 12. This is 14-bit. And take out the last 2 zeros. So when you are doing an address calculation, you will always find this last 2 bits to be 0, because you see your instruction addresses are always divisible by 4. Right? It is always divisible by 4. And that's why always you will find a 0, 0 at the end. So your target bit pattern, 16-bit pattern, is really this one. Now what is that? This is in decimal. If you see, this is like -5. 16-bit 2's complement, if you convert that bit pattern into decimal, it's -5. That means my machine code is going to be your opcode is what? Let's look at the MIP screen sheet page. BNE opcode is, I believe all you have the access to that page. Please, if you don't open it, just open it and look at BNE is 5x. Opcode 5, which is 6-bit, 0, 0, 1, 0, like this, and then RS. So mnemonic for this guy is this, right? BNE, RS, RT. So that means T0 is RS, T1 is RT in this case. So this is my, okay, RS equal to $T0. And if you look at, there is a table in that green sheet page that register name to the numbers. T0 is register 8. So it becomes like in decimal 8, which is in the 5-bit 0, 1, 0, 0, 0. RT is my T1, which is 9 from that table, which is 1001. And my immediate is this guy, which is 1, 1, 1, 1, 1, 1. 11111110 11. Now you put together all these machine code together, 0 0 0 1 0 1, followed by RS 5 bit 0 1 0 0 0, RT 5 bit 0 1 0 0 1, immediate 1 1 1 1 1 1 1 1 1 1 1 1 1 0 1 1. Now change it to the hex. So this is the machine code anyway. Computer will understand that. Your processor will understand that. But for us, let's represent that in a hex. Group by 4 from the LSB side. 4, 4, 4, 4, 4. Okay, so this is like 1, this is 5, this is 0, this is 9, this is F, this is F, this is F, and this is 8, 10, 11, AB. Yeah. So your machine code for this guy is hex 1509FFFB. Is there a question so far? Okay. Now let me give you some trick with a mental calculation. Okay. It's if you see, we are always dropping these 2 zeros. What that essentially means in terms of mathematical operation, we are taking the BA, okay, and doing a BA by 4. Sorry, 4. BA by 4. So in fact, so this is 3. Yeah, I think so. Yeah, BA by 4. So here BA was 20. So BA by 4 minus 20, BA by 4 would be minus 5. So instead of like doing this bit pattern expansion and do this calculation, you can simply do a BA by 4, that calculation, and make this guy as a 16-bit 16-bit 2's complement of minus 5. Okay, 16-bit 2's complement of minus 5 that you can do is to make the problem a little bit simpler for you. Okay, 1 0 1. Okay, so this makes sense. Okay, now let's do the same problem. Let's keep this observation one more, and let's do the same problem. Just change it to, let's say, L2. Like L1 was a backward jump, right? We're jumping back, test and jump. Let's make it a forward. Just let's do that problem. What if it was forward? So in this case, what we are going to do, we know the PC next in this case is now 0 4 0 0 0 0 2 0. That's the L2, right? And we know the PC current is the same. Which is 0 4 0 0 0 0 1 0. That means my BA in this calculation would become PC next, which is 0 4 0 0 0 0 2 0 minus 0 4 0 0 0 0 1 0 minus 4. Take a hex calculator, do that calculation. So it will be like 4 zeros. 4000020 minus 4000010 minus 4, which is 12. Like, okay, that minus is 14, 16 minus 4, which is 12. That means my immediate is BA by 4, which is 3. Okay. So in that case, my immediate bit pattern is going to be 16-bit 2's complement of 3. Okay. Now let's do another round of simplification of this whole problem. You see, I have, for a forward jump and backward jump, I have two numbers here. Just relate it, right? We are in the previous instruction when it was L1, like we are jumping to an instruction which is like 4 instruction away, right? It is a -4. For that, we calculated become -5, and if it was a L2, it was an instruction 4, but instruction was calculated to be 3, right? This immediate value. So in a sense, we can actually do very shortcut method just by counting the numbers instruction, okay? So first of all, am I jumping forward or jumping backward? If I am jumping backward, let's count the instruction. 1, 2, 3, 4. I'm jumping back 4 instructions. So my immediate value is minus 4 plus 1, which is -5. Now, if I am jumping forward, count the instruction 1, 2, 3, 4. Fourth instruction, subtract 1 from it, and that always becomes your immediate instruction. So once we understand the whole process, how things are calculated, we can actually pretty much simplify for the mental calculation for it. We simply count the instructions, okay? If it is a backward jump, we basically increase that index by 1 and do the negative of it. So in previous instruction 4, add 1 more, 5, make it a negative. That becomes my immediate, -5. Now, if it is a jump forward, count the instruction, reduce by 1. So if it is, in this example, it is jumping forward 4 instruction, reduce by 1, which is 3. That becomes your immediate 16-bit. Question? Okay. Now let's do this thing. Same example. Let's do how the jump instruction calculation would look like. Okay. So for that, let me how we can do that. Can I copy this frame? Let's see. How can I copy everything? Okay, let me save that frame as image. Hey, why cannot I save it? Hey, just hold on, let me set this up. Just hold on. Stop sharing. I will download this PDF. Okay, that's okay. Let me take a snapshot. Okay, save it. Okay. All right, let me share back. No, this one. Okay, I have taken the screenshot. I'll upload it in the discussion. Let me just erase all the irrelevant part of it. Okay, hey guys, I have an idea. Why don't you guys take 5 minute break? Let me set it up for the next discussion, and after 5 minutes we'll be back. Okay. Okay, I'm ready. Let's come back with that discussion of the jump address. So let's look at this example now. So similar example, just I replace the instruction 3 with JL1. So we are basically trying to jump back to the L1. Now here, the rule is your PC next is constructed with the PC current, which is like here, plus 4, which is this one. We pick up from this bit pattern the most significant 4 bit, followed by the bit pattern in the jump address, followed by 20. Okay. So PC next has to be, so your jump address has to be such a bit pattern. If you put the bit pattern here, then PC plus 4, take the 4 most significant bit and add 2 zeros at the end, you end up in a target address, which is for this example, your target address is this one, right? So in a sense, let's do it. Your PC next we all know PC next is going to be like this guy, right? Which is, if we expand into binary, 0, 0, 0, 1, 0, 0, 0, then 0, 0, 0, 0, 0, 0, 0, 0, 0, 4, 0, 0, and 32 bits. And your PC current plus 4, this is this guy, right? So which is actually this lower bit really does not matter that much. Oops, 0, 0, 0, 1, 0, 0, 0. So this guy, your PC next, when it is being constructed, your this 4 bit basically is this 4 bit. Okay, this 4 bit goes there. So this is like 0, 0, 0, 0. That comes from the PC current plus 4, that bit pattern. And last bit patterns are automatically appended by the processor, right? So your target bit pattern for the jump address then is this 26 bit. This is 26 bits. Let's count 1, 2, 3, 4, 5, 6. This is 28 bit. How come it is 28 bit? Just hold on. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. 32 bit. 2 bits are just dropped off. 4 bits are dropped off. Then 1, 2, 3, 4, 6. It is 28. Hey, I'm doing something wrong. 1, 2, 3, 4, 5, 7, 8.
I think the second group bits is wrong.
Second group, which one?
In PC next.
This one is wrong, you mean? Second group is
I think
something.
you might have put an extra 0 for
Yeah, that's what I'm trying to figure out. Like this is a group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, right? So we have 32 bits, right? Here.
But group 2 has 5 bits.
I see. This guy, right? Okay. Then what is happening? 1, 2, 3, 4, 5, 6. Oh, yeah. Okay, okay. So now it is 26 bit. Okay. All right. That's the mystery. I was counting 27. Why it is that? Okay. So this is 26 bit. So that means my machine code is really going to be, if you look at that green sheet page again, jump machine code is 2 hex. Jump machine code is 2 hex. So that means it is 0, 0, 0, 1, 0. It is 2, 4, 5. Yeah, this is 6 bit, followed by this part. Okay, followed by this part, which is 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I think it's all zeros, right? Yep. So your machine code really is going to be, for this case, group by 4, group by 4, group by 4. So it's 0, this is 9, really 0, 9, 0, 0, 0, 0, 0, 0. So this is going to be your machine code there. So Troy, does it make sense now? How do you compute back? Like if it is involved with a J?
Yeah, it makes more sense.
Okay, so in most of the cases, like PC plus current plus 4, that computation doesn't make any change for the most significant 4 bit, unless your PC current in such a way that if you add 4, it's going to change one of these higher 4th bit. If that is the case, then you need to be very careful of. But most of the cases, at least for the small example programs, like these bits are basically same as the PC current. PC current and PC current plus 4 most time has the same bit pattern. So that's one shortcut. Maybe you need to consider if it is a mental calculation comes into place for short questions. But other than that, you need to pretty much, if it is a big higher point questions, then, or a problem, then you need to explain it, like why you are getting that bit pattern. You are using this formula and you are determining those bit patterns, and then you are cutting out the jump address out of that 26 bit. How you're doing it, you need to explain it. Okay, what else?
Hi, Professor.
Yes.
Can we go over some the quiz question? I have one of the question, just don't know how to figure it out.
Yeah, sure. Tell me which question number.
The quiz 2, the question 17, the one we need to count the big Indian, small Indian for the address. So I really confused about that part.
Okay. Quiz 2. Okay, just hold on. Let me just take a look. Question number?
17.
17. Okay, let me go there. So it talks about that some var A, var B, that label with the byte, word, ASCII, that question?
The one we need to figure out the address.
Oh, okay, okay. So this question looks like this, right? Let me just share the screen. Okay, you're basically we need to figure out the addresses of this level. Okay, so for this question, first of all, it says where it starts the data address, right? Dot data address starts with. If it is not given, then you need to consult back your MIPS screen sheet and look at what the default MIPS assumption is. But nonetheless, you got a start value. So your var A, that first level, starts from that address. Okay. And then address B. So what assembler does at this case, so it starts from this address, and place a byte value onto it, on that address. So that address contains a byte value, and next free address is, so let's track it down, next free address is 0 cross 1000001. Now comes to the var B. Okay, var B. Var B is trying to put a word, and with a default alignment, a word type, if I want to place a word into a memory, that word must be starting from an address divisible by 4. So you ask yourself whether this is divisible by 4 or not. Next free address is 10000001, but it is not divisible by 4, so var B cannot use it as a starting address. So it has to start from an address which is divisible by 4 by alignment rule. And what is the next free address which is divisible by 4? It is 10000004. So that's going to be your next address. So now what is your next free address? Next free address is this guy. No, not this guy. Wait a minute. Not this. So this var B starting at address 0004, and it will occupy 4 byte. A word is a 4 byte long, so it will occupy address 4, address 5, address 6, and address 7. So next free address is going to be 10000008. Now the var C comes down to the var C, that level. It is placing a dot ASCII. So dot ASCII is nothing but placing bytes. The ASCII code of A is 61, ASCII code of A is 62. So this is equivalent to this statement. So practically saying it is placing ASCII, placing byte information on that next free available address. And alignment rule says byte type data can start from any address. So it doesn't matter. It basically place it onto here. And how many bytes it will occupy? Since it is of 2-character string, and it is ASCII, not ASCII Z. So ASCII will just number of characters in the string, that many bytes it will occupy. So next free address is 10089 A. So it will var C, that data statement will occupy 2 bytes. So address 8 and address 9 will be occupied. So address A would be next free address. Now var D is a word. Can I place a word at this address? It's not, right? It is not divisible by 4. So what is the next free address divisible by 4? It is 100000C. So that's what you place there. And that's how you calculate the label address. Is that okay? Well,
can you repeat again why the next address is 100008? I was kind of confused on part. For our
So
yeah.
your var B is starting from this address, right?
Yes.
And var B is placing a complete word,
Yeah.
which is 4 byte.
Mm-hmm.
So that means from this address 4, address 5, address 6, and address 7 will be occupied.
Oh, got it.
Right? So if you want to draw a picture of the memory, let's say this is my address 0 1 0 0 0 0 0 0 4. So you are occupying this address and you are placing this data 98765432. So it is a, let's say it is a big endian. So 98 will be placed there. Then 76 will be placed there. Then 54 would be placed there. And 32 will be placed there. So your var B is really starting from this address, but it is occupying 4 byte. So occupying till 7, right? So your next free address is this guy.
Oh, okay. Got it. And also, do you mind go over question 15 too?
15. Okay, let's see. Okay, it gives a snippet of a memory address and big endian, little endian from that data. Okay, so it looks like this. So, okay, so this question says that if I access a memory following a big endian convention from the address 10010004, so I'm trying to access from this point, okay, in a big endian and little endian convention, right? So first of all, read always happens from multi-byte read always happens from lower address to the higher address. So we start reading from here and we are trying to read a word, right? So a word is 4 bytes. So we are trying to do a multi-byte read. So it will be read in this way. So all these 4 information will be reading, right? Byte 1, byte 2, byte 3, byte 4. Now the question is how we arrange these numbers into a value representation if it is a big endian system and if it is a little endian system. Big endian system assumes your most significant byte is in the lower address. So this guy is MSB for big endian system. And this guy is LSB for a big endian system. So your value is really BA809875. Whereas little endian system, just go with the opposite assumption. This is LSB for a little endian system. Let's see, we're talking about the little endian here. LSB, and this comes as a MSB. So for this little endian system, the value is really 759880BA. Make sense?
Yeah, I got it. Thank you very much.
Okay, what else?
Actually, I had a clarification question about the programming assignment 6.
Yes.
On the requirements, it says that the entire program needs to have 2 JLs. Does that include like the JAL you put in the main code, or does that mean we have to add 2 of our own?
Okay, the assignment, right? This is recursive LCM.
Yes.
Recursive LCM. Let me see what is that implementation looks like. Let me see JL usage. Yeah, so entire program has 2 JL. So that means you already has 1 JL in the main. So your function, recursive function, will have 1. That is the best implementation actually. You don't need more than 1 actually in your implementation.
So just 1 in our own code, right? Like
Yes.
in our part. Okay, thank you.
Yes. That is the most optimal coding that you can make there.
Yeah, I was a little confused by the way it was worded.
Okay. So if you don't have any questions, we have another round of review next day. So your practice midterm, I think, will be up tonight after 7:15. So you can go through further, and I hope you will be studying more onto this and have more questions. Please update on the discussion, midterm review discussion, so that we can discuss more on your doubts next day. Is there any other question, or we can stop tonight?
I'll probably have some at office hours, so I'll have to do that like, privately, like with an appointment, right?
Okay, so if you don't want to ask in front of class, then yeah, you can come to my office, or of course you need to make an appointment. I think, yeah, Tuesday is for my other class, but you can send me an email and I'll accommodate it.
I have a question.
Oh, so yeah, you can go ahead.
Yeah. On quiz 3, question 11, it says ADI is a pseudo instruction. Can you go over that again?
So did you notice what is the immediate field value, number of bits you need to represent that immediate field value? So how many bits you need for that question? Question number, what you said? Question number
11.
11. Yeah. So how many bits you need there? Tell me. 20AB3. To represent that, how many bits you need?
I'm not sure.
So it says it has 5 hex digit, right? 20AB3. So total 5 hex digit means you need multiply by 4 means 20 bits. So 5 hex digit is 20 bits. But your add I, the basic instruction, if you remember the instruction format of the add I, is the immediate value is 16 bit. That means this immediate value cannot be placed into the basic instruction. So your assembler will recognize that and will immediately use an pseudo instruction expansion on that instruction. So that add I at that point will be treated as a pseudo instruction, since your immediate value cannot be fit within 16 bit. Make sense?
Yeah, thank you.
Yeah, you can write that code into your Mars assembler and see what my assembler does. Yeah, so you need to make, yeah, you always need to make sure that the code you are writing there, if your immediate field is not going to be fit into 16-bit representation, signed representation, or unsigned representation, depending on if you are using a logical instruction or an arithmetic instruction. Depending on that, if it cannot be represented with 16-bit, assembler is going to treat that instruction as a pseudo instruction and put like 2 or 3, depending on what instruction you are trying to achieve, put 2 or 3 basic instruction for that to achieve that goal. Okay, what else?
Could you also do number 4?
I-type instruction in MIPS may use which of the following addressing mode?
No, the one that's executing a jump when PC contains the that one.
So
Yeah.
this guy is the reverse one that we just did on the jump instruction, like how we make the jump instructions machine code. It is just the reverse problem of that. It says it already given you that jump address value. So it is something like this. So you are given this thing. So your jump address, the JA part of it, where is that? Here. So this part is given in this problem. Is this part. Okay. So that means essentially your 26-bit. So if you make it a binary representation, 3 is 0011, A is 1010, excuse me, 3 is 0011, 8 is 1000, 7 is 0111, F is 111, 8 is 1000. Now that's 28-bit. So make it 26-bit, just shade off these 2 bits from beginning. So that is your 26-bit. And now your PC, so that is your jump address. Okay, let's mark it. That's your jump address. Now PC plus 4, my PC contains this, right? So PC plus 4 would contain what? BC, right? PC plus 4. It really doesn't matter probably in this example, but PC plus 4 would be 02A 8956 BC. 8 plus 4 is 12, which is BC, which is C, which is okay. Now, which is what? Which is this thing, right? 00 00 10 1010, 8 is 1000, 9 is 1001, 5 is 0101, 6 is 0110, B is 1011, C is 1100. So this is your PC plus 4-bit pattern. So your our rule says target address will have 4-bit pattern out of this, followed by this 26-bit pattern, followed by 2 zeros, followed by 2 zeros, followed by 2 0. So you construct that. This is 2 0 and 4-bit coming from the PC, 4-bit coming from the PC, which is 0010. Right, so this guy coming right over here. We're adding extra 0, and that becomes your full 32-bit. Now change it to your the hex address of this. So how do you change it? Just group it by 4. 1, 2, 3, 4. 2, 3, 4. Did I do something wrong? Let me see. So this one. Okay. So 1, 2, 3, 4. There, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 4. Yeah. 1, 2, 3, 4. Okay. So this is E. This is 8. This is E. This is 1. This is F. This is E. This is 0. Is it something? Oh, I forgot this one. This is 2. So 2E, 8E, 1F, E0. So this is your ultimate address, target address that instruction is going to be executed from this address. Or jump is going to that address basically 0, 2, E, 8, E, 1, F, E, 0. Is that clear?
Yeah, that helps. Thank you.
So you need to really like make conversion to the binary from the hex and cut out the patterns or rejoin the patterns according to the problem. So this problem, we basically rejoin, we cut out part from the PC plus 4, have that bit pattern from the instruction and added 2 more bits and then constructed the address, which is just reverse problem of this guy, where we know the PC next, what is going to be. From there, we cut out that 26-bit pattern out of it. You make 26-bit, take this 26-bit pattern and put there as a jump address. So just a reverse problem of that. Okay, anything else? If not, then good night, everybody. See you on next day, next week. Make sure to jot down your questions on the discussion so that we can discuss more on your doubts and queries.